Okay, so here's another example problem. This time we've got a radioactive substance and it's going to decay. So what that means, when you have a radioactive substance, that means that it's emitting particles, and as it emits particles, it changes into something else. So you're going to have less of the radioactive substance than when you started. So decay means that it's going to get smaller. So we see here, we're given our model, we see that it's negative. Remember, we're going to have a negative rate if it's getting smaller, so that all checks out. T is our time in years, and A is our amount in grams. So this is a pretty typical setup for radioactive decay. All right, so here's our three questions again, just like we did last time. A, what is the amount of the initial sample? How much do we start with? Okay, here's our sample, our standard setup. Remember that A naught's our initial amount. The number in front is our initial amount, and so we don't even have to do any work for this one. We just have to remember that it's the number out front, and it's 200. Now, if you forget that, you can always plug in T equals 0 like we did last time, and you'll still get 200. Okay, part B, how much is left after 50 years? How much is left after 50 years? So are they giving us a time or an amount? Okay, 50 years is definitely a time. So we're being given that, that's our answer for part 1. We're being given that T is equal to 50, and so we need to find the amount, so we're going to go ahead and plug that into the model that we're given. So A is equal to 200 e to the minus 0.05 times 50. We're going to put that into our calculator carefully. That should be a 50, not a 56. Okay, and when we put that in, you should get 16.42. Rounding to 2 decimal places, you should get 16.42, and our amount is in grams, so this is also in grams, and this was also in grams. So we started with 200 grams, and after 50 years we've got about 16 grams. Okay, so our quantity is getting smaller because it's decaying. Okay, so that's our answer for part B. All right, let's look at part C. What is the half-life of this isotope? Oh, what do we do with this? They're not even giving us a number. Okay, so we need to know what half-life means. Half-life means the amount of time that it takes to get to half of what you started with. Okay, so the amount of time that it takes to get to half of what you started with. So half of what you started with. Okay, and this is an important concept with radioactive substances because we've got to be careful with where we put these things, right? We can't just leave radioactive things laying around, and the faster they decay, the more dangerous exposure to them is, and the longer they take to decay, the more careful we have to be with where we store them and what we're going to do with them long term. So this half-life concept is very important when we're talking about radioactive substances like in chemistry and physics. Okay, so if we're looking for half of what we started with, that means we need to know what we started with. We started with 200 grams, so we are looking for 100 grams, okay? Half of what we started with. So you have to know what you started with, and then you're looking for when you reach half of that. Okay, so now we know that we're looking for A is equal to 100, so we're going to put that in here, and we're going to look for time. So we're going to have 100 equals 200 e to the negative 0.05 t, and we are looking for time. So this looks just like part C of the last problem that we did. We need to get the exponential by itself, and then we need to take a logarithm. So first thing that we do is we divide by 200, and we're going to have 100 over 200 equals e to the minus 0.05 t. All right, and remember, in order to get this out of the exponential, we're going to have to take a log on both sides. Okay, so coming up over to here, we're going to have natural log of 100 over 200. Now these fractions, you can simplify them, you can change them into a decimal or whatever, but it's going to go in the calculator in the end, so it's fine just to leave it alone. So we take a log on both sides, we get ln of 100 over 200 equals ln of e to the minus 0.05 t, and what do we remember about natural log and e? They cancel out. So we get natural log of 100 over 200 equals negative 0.05 t. We want to solve for t, so we divide by negative 0.05. Okay, now we're going to put this in our calculator very carefully. Okay, we're going to make sure that we have parentheses like this, divided, and you should get 13.86. 13.86 equals t. Okay, and time for this problem, time is in years. So this is years. All right, so it's going to take almost 14 years to get to half of what we started with. Okay, so 14 years will have half, 28 years will have a fourth, another 14 years is 42, I think. We're going to have an eighth, and so on. So it's going to cut in half every 14 years. All right, so let's check this one. We started with 200 grams. At 14 years, we come next. 14 years, we have 100 grams. And at 50 years, we have 16 grams. So you see this time our amounts are getting smaller and smaller, and that's what it means for decay.